Hello everyone, welcome back. In this section, we're going to work with what may be the most important part of our microservices app, and that's the messaging queue, also known as the events bus. This event bus connects our microservices, so it's very important that it be resilient. We're going to use RabbitMQ for this purpose. When we're working with microservices, we want to keep our individual microservices able to function independently. So in case one of them crashes, the others can continue to operate and provide some functionality for the user. So in order to do this, they have their own separate databases and their own separate routing. They're completely standalone. Now, in order for them to share some data, since they have separate databases, they need some way to send that data between the different microservices. And to do this, we use an event bus or a message queue. The way a message queue works is basically that when one of the microservices experiences some kind of change to its data, it then wants to emit an event that describes that change. And then this event will flow from a service to the message bus. And then from the message bus, it'll flow to another service. And that service can then read the description of the change and make the appropriate changes to its own database to reflect the updates that have just happened. This can lead to a lot of problems when we're using async communication in our microservices. For example, we have an event called ABC, and then we have another event happen, which we could describe something happening as XYZ. So the ABC event, maybe it's very important for that event to register before the XYZ event. And in a lot of cases, these events are just going to arrive out of order. A million things can go wrong. One service could be offline. A file could be locked while it's being accessed by another service. Maybe one of the services is overloaded and running really slow. And then a different service is running very quickly because it has a light workload. So depending on which services processes which event, they could arrive out of order for many different reasons. And this is going to cause a lot of problems. So how can we fix this with our async messaging flow? Well, in the next lesson, we're going to look at how to fix that with the very architectural design of our microservices app itself. Okay, thanks a lot for listening. I'll see you then. Hello, everyone. Welcome back. In this lesson, we're going to take a more in-depth look at some of the concurrency problems we have with async communication with our messaging queue, and we'll look at how to solve them using the architecture of our app. All right, let's get started. We'll have to design our app in a special way, and we have to have it set up so that each service completely owns its own resource. The service is going to be the canonical authority on that resource. And that database of that service is the database that is the authority on everything related to that service. So a network request comes in. It's CRUD, create, read, update, destroy. It's sent to the service that controls that API. And that service is the canonical authority. It can then emit an event that describes the changes that were made, and that event is then emitted to any services that are subscribed to listen to our message queue service. If a service completely owns its own resource, then it's able to do a number of things. It's able to generate a version number for every event that happens, and this version number is going to allow us to keep track of concurrency and make sure that our events are registered in the proper order. In this case, we can set up some rules ahead of time that let the services know that they have to process these events in order of their version number to make sure that things happen in the order that we want them to. So now let's say that we've got two different services. One of them is emitting some events and the other is subscribing to the message bus. So we've got an event for ABC and it's version 1, and then we've got event XYZ and it's version 2. So let's say these events are emitted at about the same time, and they both flow over here to the message bus. And let's say the message bus sends this one out to the subscribing service, but let's say at this time the subscribing service is offline, so this gets rejected and sent back to the message queue. In the meantime, XYZ is emitted, flows up here to the subscribing service, and now maybe the subscribing service is back online. So it's going to accept this event, XYZ, and it's ready to process it. But it's going to check the version number first. It's version 2. It's going to subtract 1 from that and say, hey, do I have version 1 in the database already? No. So it's going to reject this. Send it back to the message queue. In the meantime, the message queue is going to re-emit the first event, and it'll flow back here to our subscribing service again. This time the subscribing service is back online. It's going to take event ABC. It's going to see that it's version 1, and it's going to accept this event now, because when it subtracts 1 from 1, it gets 0, and it sees that, well, yes, this will be the first event. Next, when this event is re-emitted, it too will be accepted, because now in the database, it has version 1 as the last version that was here. So next, it gets XYZ. It sees that it's version 2. 2 minus 1 is 1, and 1 was processed last, so it accepts this one. And that way we make sure that all the events happen in order. Well, that's like a basic summary of concurrency problems. In reality, it's so complicated and so many things can happen that you'll just pretty much have to take my word for it that async communication concurrency problems can be a major issue. And that's why we're careful to make our services a canonical authority on the resources that they can control. In this way, that canonical authority over here gave our events a version number. And these were generated by the database itself. And that version number assures us that these events can be processed in the correct order. All right, that's it for this lesson. When you come back next, we're going to work on putting this all together with RabbitMQ. All right, thanks a lot for listening. I'll see you then. Hello, everyone. Welcome back. In this lesson, we're going to use RabbitMQ to create our message queue. And the message queue is going to take our events and send them between our services so that our microservices can communicate. Now, RabbitMQ with Kubernetes and Docker can be a very complex subject. So we are going to start with the very simplest setup that we possibly can using Kubernetes and RabbitMQ. Here are the URLs for the RabbitMQ homepage and the Docker Hub image that we are going to be using. In the next step, we're going to use the RabbitMQ Docker image, and this is where we get it from on dockerhub.com. Scrolling down, we can see some of the different packages available. We'll be using 3.8 management, and you can find out a lot more about it on this page. Let's get started by creating our YAML for RabbitMQ. If you have Scaffold running in a terminal window, you can just click into that window and press Control-C to stop Scaffold, and it will perform its cleanup operations. And what that does is delete the pods and services that we created earlier. So now we have a clean slate. Now in our config K8s directory, we are going to create a new file, and let's name it RabbitMQ-statefulset.yaml. We're going to type in API version apps v1. The kind for this is stateful set, which is required for RabbitMQ. We'll name it RabbitMQ stateful set. We want to give it the label app::RabbitMQ. We're going to just pull the default Rabbit container from Docker Hub that's named RabbitMQ version 3.8-management. We're going to use the default ports for RabbitMQ. We use AMQP on port 5672. Here's where we can configure a little bit of a liveness probe. We basically want to test if RabbitMQ is up and running. We can do a ping. And we set up another diagnostics here for check port connectivity. So this will give us our basic liveness test. Now we'll do a YAML separator and create another object here for a service so that RabbitMQ can communicate. Type is going to be load balancer that we use with RabbitMQ. And we're going to put it on the same ports we used earlier. So that's our very basic configuration that we can use now. Now open a terminal. It'll be in our root directory, bird squawk. Let's run scaffold dev, and that will start all of our Kubernetes clusters and services that are described in our YAML files. Let's open another terminal in the same directory, and we can use the command kubectl get pods. Kubectl get services. So we can see we created a new RabbitMQ stateful set pod and a RabbitMQ service to go along with it. I think that's a good place to break for this lesson. When we come back, we're going to work on setting up Ingress Nginx, which is a load balancer that'll allow the outside HTTP requests to come in and access our Kubernetes cluster. Thanks a lot for listening. I will see you then. Hello, everyone. Welcome back. So far, we've got our microservices running inside the Kubernetes cluster, but we have no way for the external world to reach them. All of these microservices are on some random IP address that Kubernetes assigned. Now we'd like some way for an HTTP request to come in and find the proper service. To do this, we're going to use Ingress Nginx. Ingress is a Kubernetes API object that allows us to take an external HTTP request and route it to the proper microservice within our Kubernetes cluster. It can also provide load balancing, SSL, and some other network features. Later in this lesson, we are going to create an Ingress YAML file, and we'll be able to configure the routes for our API inside of there. Here's a website you can take a look at for some information about Ingress. Let's have a look at that website so we can see how to install Ingress Nginx. Here's a command we can use for Docker, Docker desktop. If you're using Minikube or another setup, there are other commands for you to run. I'm going to go ahead and install this on my system. I'm on a Mac, so I copied the command for the Mac, and I'll just paste it right into my terminal and hit enter. Now let's go back to that Ingress Nginx page we had open. Scroll down near the bottom and look for the command to check your installation. Copy and paste that into a terminal. And you should see this result. To stop watching Ingress, we can just press Control-C. So that's a successful installation of Ingress so far. Now let's create a new file in our K8s directory and name it ingress-service.yaml. We'll start typing API version network.k8s.io/v1 kind ingress. Metadata. The name of this is Ingress Service. In this annotations section, be very careful of your spelling. Here we are going to put in kubernetes.io/ingress.class:\Nginx. And for the spec, we have rules -- for array and host : bird squawk -app.dev. Now this is going to be the URL for our app. So this is a pretend URL. Next, we're configuring our API routes within this rules. We're going to use the API bird squawk get that we configured earlier. And it's going to communicate with that API through the bird squawk service, which is the cluster IP service that we use to communicate with pods inside of Kubernetes. And remember, we configured that to be on port 5000. Okay, now that we've got our YAML typed in for the Ingress service, let's get a new terminal open again in the root directory and start up Scaffold with the scaffold dev command. And then Scaffold will run all of our YAMLs and apply them. Well, we've installed and set up Ingress. Let's take a little break now. And when we come back, we're going to work on connecting these puzzle pieces together so that we can have some communication from the outside world into our microservices that live in the Kubernetes cluster. Okay, thank you very much for listening. I'll see you then. Hi everyone, welcome back. In the last lesson, we set up Ingress. Now we need to connect Ingress to some of our services that we've created in our app. Next, edit the host file on your local machine. Here's where you can find the host file depending on whether you're using Windows, Mac OS, or Linux. In Windows, make sure you open your text editor with administrator permissions. In Mac and iOS, you can enter your password. I'm on Mac OS, so I'm going to open a new terminal and use the command code etc hosts. At the end of the hosts file, I add the following entry: 127.0.0.1 space, and then the name of the URL that I'm using, bird squawk-app.dev, and this will redirect this URL to our local host IP address. Retry as sudo, and I can enter my password. One thing to note is that if you're using Minikube, instead of this address, you need to use your Minikube IP address. To do that, you can use the command Minikube IP and then paste that number right here. Now let's open a new terminal and use the command kubectl get ing. This returns our Ingress service that we just created in our YAML file, and it tells us it's running on port 80. This brings us to the issue that you have to make sure that nothing else is already running on port 80. To do this, you can Google how to kill a service that's running on a port for your operating system. Now let's open a new terminal and use the command kubectl get ing. This returns our Ingress service that we just created in our YAML file, and it tells us it's running on port 80. This brings us to the issue that you may already have a service running on port 80 on your machine. You'll have to kill that service first in order for Ingress to work. So just Google how to kill port for your operating system. Okay, let's go ahead and try this now with Postman. Create a new tab. Let's enter the URL birdsquawk-app.dev. With the path API birdsquawk get. Click down here to the headers section. For the key, we want content type. For the value, application JSON. Cool. Let's click on send. And here it returned the proper greeting, hello, which we defined right here from birdsquawk. So did that make sense? Can you follow what happened? How did our request get from Postman to birdsquawk and back? Postman sent the HTTP request into Ingress. Ingress took a look at the route of the API path we entered and decided that that route should get sent to Kubernetes cluster IP service that connects to the pod that has the container with our birdsquawk microservice running inside of it. And the birdsquawk microservice sent back some JSON as a response, and that went right back to Postman for us to see. Okay, let's take another break. When we come back, we're going to get into the details of working with RabbitMQ message queue service using topics. Thanks a lot for listening. I'll see you then. Hello, everyone. Welcome back. You might recall we're using RabbitMQ for our events bus. And now we're going to look at how we configure RabbitMQ. RabbitMQ has several different message exchange types, but we're going to use the topics exchange. At the most basic level, the message exchange pattern we are using is called publish subscribe. In this pattern, we have a set of publishers and a set of consumers that subscribe to our message queue. RabbitMQ provides the role of sorting these messages and sending them to the proper queue. It does that using a routing key that's attached to every message that's published. The messages are sent to the exchange within RabbitMQ. The binding rules then sort the messages according to their routing key, and the messages are then sent to the proper queue. Consumers can subscribe to the queue, and then they will receive the message with its associated data. For topic exchange, we can use wildcards for our binding patterns. A star is equal to exactly one word, and a hash is equal to 0 or more words. In this example, Q1 is bound to the pattern star.brown.star, and Q2 is bound to the pattern star.star.fox, and also the pattern lazy.hash. Let's look at quick.brown.fox. It'll match this pattern, and it'll also match this pattern, but not this pattern. So it will go both to Q1 and Q2, here and here. What about this one? Lazy.brown.dog. It'll match this pattern. It does not match this pattern, but it does match this pattern. So again, this one can go to both this and this. It'll get sent to both queues 1 and 2. Let's look at quick brown cat. It'll match again the top pattern because it's got brown, it does not match the fox pattern, and it does not match the lazy pattern. So it only goes up to the top. What about lazy.red.rooster? It doesn't match this pattern. It doesn't match this pattern, but it does match this pattern. So it just only goes to the bottom queue. And so this is how we can use routing keys and routing patterns in order to sort our messages to the various queues. If a message doesn't match any routing pattern, then it's just not going to go to any queue and it will be discarded. So with our Bird Squawk app, we are going to use the topic exchange type with RabbitMQ. It's basically a publish subscribe model, and each message will be sent with a routing key. And then we'll have some routing patterns that will sort the messages to various queues that our microservices can subscribe to. In the next lesson, we're going to do a summary of everything we've learned so far about installing RabbitMQ, connecting it with Ingress, and using topics to sort our messages. Thanks for listening. I'll see you then. Hello, everyone. Welcome back. In this lesson, we're going to review everything that we've learned so far about RabbitMQ. RabbitMQ is a message queue service that we're going to use for our events bus so that our microservices can communicate with each other. Since our microservices need to be standalone and have their own databases, the only way for them to share data is by emitting an event whenever a change happens. And that event is a description of the change that has just happened. That event can flow to the event bus, which is a message queue service. We can have a lot of concurrency problems happen, which is when events arrive out of order. Lots of things can go wrong in a system. A service might be offline or a file might be tied up. So another thing that could happen is one service could be busier than another and run slower. So these are all reasons events can arrive out of order. To fix this problem, we have to actually structure the architecture of the microservices in a special way. We have to make sure that each service completely owns its resource. Using this pattern, each service is a canonical authority on the resources that it owns. Now we can generate a number here for each event that happens. So let's say event ABC. We give it a version number 1, and then maybe the next event is XYZ. We would give it version number 2, and these version numbers are generated automatically by the database. Using this kind of architecture allows us to ensure that these can be processed in order later. With RabbitMQ, we are using a type of exchange called topic exchange. And with topic exchange, each message has a routing key, and then the routing key is used to sort the messages into different queues. When we sort the messages, we use these wildcard rules, where a star is equal to exactly 1, and a hashtag can be equal to 0 or more words. And so our binding is done with these routing rules that we create. Up next, we have a short quiz to test your knowledge on RabbitMQ. Then, in section 6, we're going to complete our app, and we'll be able to see how all the pieces work together. Thanks a lot for listening. I look forward to seeing you then.